Welcome to our talk on our recent short paper, In-Context Quantile Regression from Multi-Product Inventory Management using Time Series Transformers. In this paper, we are looking at inventory management, specifically the news vendor problem. In the news vendor problem, you try to find an optimal order quantity Q, given that you have some features X and a cost structure C. The special property of the news vendor problem is that if you order too much, you have a different cost than if you order too little. And this means that the news vendor problem can be translated into a quantile regression problem where you look for the target quantile alpha. Current approaches from operations management have two major shortcomings. Number one, they would typically train such a quantile regression model for each specific product. This means if you have thousands of products, you need to train thousands of models. And whenever you get a new product, you have to train another model. Number two, they are typically trained on specific quantiles, let's say the 70% quantile. But if your cost structure changes, your target quantile changes, and again you have to retrain the model from scratch. To remedy these issues, we propose to combine in-context learning with simultaneous quantile regression. What this means is we have a set of tasks, and each task, in our case, means solving a news vendor problem repeatedly for a single product. Based on this task, we get some input for each time step t in a task that we give into our model. And during training, we try to find the optimal parameters of that model. There are two things we are doing here. Number one, we use simultaneous quantile regression. That means we add the service level alpha into the prompt, into the input, as if it was a feature. Then during training, we sample this service level randomly between 0 and 1, and we also condition our loss function on that service level. And what this means is that in the end, our trained model is conditioned on the service level, which means if the service level changes, then you just need to change the input in the prompt, and the model will adjust the quantity accordingly without having to retrain the model. Number two, we leverage the in-context learning capabilities of transformers. What that means is to make an order prescription for a specific product at a specific time step. We give it a rather long input prompt. Let's say it sees the last 50 observations. Plus, during training, it sees all these prompts across the different products. And what this means is that we train our model essentially as a meta-learner, so it learns really how to extract information from a prompt. And this means if we get a new product, or whatever properties of the product change, we just need to change the input prompt, but because the model has become a meta-learner, it can essentially find the right order quantity just based on the prompt without the need to retrain it on a specific task or a specific product. This means we have three major contributions in our paper. Number one, we extend the Transformers ICL capability to multivariate non-i.i.d. time series data. We integrate simultaneous quantile regression into the in-context learning framework of the transformer that gives us basically a universal quantile regressor. And we apply our model to a real-world problem at scale. So for our first proof of concept, we tested it on the M5 competition data. So these are basically demand data from Walmart. And we can show a couple of things. Number one, our model, which is the one on top, outperforms any single product models by a very large margin. Number two, the model that is trained across the different quantile levels has the same performance than one trained specifically on the target service level. That means the additional versatility does not come at a cost. And number three, the performance between new products and existing products, this is like this orange and gray, is very little, which means that we are performing on new products almost as good as we are on products that we have seen during training. In the future, we plan to extend our research further. Number one, we want to train a much larger foundation model across companies. We want to extend it to more complex decision-making problems and also work on deriving theoretical properties of our proposed solution. Thank you for your attention.